Hi, in this video, we will discuss how to calculate the triple integral. We know that mass is equal to density multiplied with volume, where the density can be represented by density function, so this function tells the density at a specific x, y, z coordinate, and the volume here can be represented by dx, dy, dz. So if we take triple integral of the density function with respect to dx, dy, dz here, then you can obtain the mass. We can calculate this triple integration in three ways like this. If you choose to integrate the density function in the z direction, then you consider yourself to look at the object in the z direction. From top to the bottom, you see the region like this. So this is the region represented by dA here. In the second case, you may consider to integrate with respect to dx first. So in this case, you look at the object in the x direction and you will see this region. So this region represented by dA here. Lastly, you can also choose to integrate the density function with respect to dy. So in this case, consider yourself to see the object in the y direction, then you will see the region looks like this. So the dA here again is represent the region area here. We can use these three approaches to compute the triple integral. If the density function and the shape of the object here are same for these three cases, then by using these three formula, you will still obtain the same mass. Let's use the type 1 triple integral formula to solve the mass for this object. In this case, the density function is equal to x, y, z squared, therefore you can substitute inside the formula. For the type 1 triple integral, we need to integrate with respect to z-axis. So let's integrate with respect to z-axis. So the limit for the z-axis is from here, where the limit here is z equal to 0 for the yz plane. And then the upper part for the z-axis is this, which is given by z equal to 1 minus y. Therefore, this is the upper limit for this object. So you can substitute z equal to 1 minus y and z equal to 0 for the limit. Since you are integrating with respect to z-axis first, so you need to consider yourself watching from top in the z direction. So when you see from top, you will see the shape like this in the xy plane. So this is your y-axis and this is your x-axis. So if you draw the y versus x here, then you will see this shape. You are looking for the area under this region. From here, we know that this can be represented by y equal to 1. Therefore, we can put the equation inside. And then for this curve is represented by y equal to square root x. Therefore, we can represent this curve here equal to this. To find the intersection point between these two curves, which is located here, so you can compare between the line 1 and line 2. Let the line 1 equal to line 2, then you obtain 1 equal to square root x. With that, you obtain the x equal to 1 power of 2, which gives you 1 also. So the intersection point is 1, 1. Previously, you have learned how to find the area under this region, where to find the area, you need to perform double integration with respect to dx dy here, or dy dx. If you integrate with respect to dx dy, you must ensure the y limit here must be a constant. So assume your y limit is constant, which is from y equal to 0 to y equal to 1 here. So substitute 0 to 1. Then your x limit is from here. So this is your lower x limit, which is equal to x equal to 0. And then this is the upper x limit. So you need to find the x. Therefore, x is equal to y squared. So substitute inside. So you can also consider to integrate with respect to dy dx. So in this case, the x limit must be constant. So if you choose the x limit to be constant, for example here, x limit is equal to 0, which is constant in this case. And then x equal to 1. So your y limit is in this direction. So the lower y limit is here, which is equal to square root x. And upper y limit is here, which is equal to y equal to 1. So you substitute 1 inside. So these two will give you the same area, which is this region. Since we know that the dA is equal to dy dx or dx dy, so in this case, you can use the same approach to find the corresponding limit. For example, if you use dx dy like this, then you will obtain the limit here. So if you choose dy dx like this, then this limit can be found from here. You can continue to solve the triple integral here, and you should obtain the mass equal to this answer. As you can see, regardless of the formula that you form, both of them give you the same answer. In this example, you have the same object with the same density function, and you are going to find the mass. So in this case, we are going to use the type 2 triple integral to solve the problem, where in this case, you can see that we need to integrate with respect to x first. So if you integrate with respect to x, then you need to find your lower x limit, which is here. So at here is equal to x equal to 0, which is also the ZY plane. Your upper limit for the x can be found from this curve, which is given by y equal to square root x. So from here you can find it to be x equal to y squared. So you can substitute the lower and upper limit in the x direction to be 0 and y squared. Therefore, you should obtain this. To find the region in the dA, you need to look at the item in the x direction here. So if you see the item in this direction, then you will get this shape in the ZY plane. So you can draw this shape similar like this in the ZY plane. From here we know that the intersection point is equal to z equal to 1 and y equal to 1. And from this curve, we know that the function here represented by z equal to 1 minus y. Therefore, this line can be computed by this equation. To compute the area of this region, we can double integrate with respect to dy dz or dz dy. If we choose to integrate with respect to dy dz, your z limit must be constant. So in this case, you have z equal to 0. For the lower limit, z equal to 1 for the upper limit. Therefore, you have 0, 1 for the z limit here. For the y-axis is in this direction, therefore this is your lower limit, y equal to 0, and the upper limit can be represented by this curve. So your y is equal to 1 minus z. That can be obtained from this equation. So you have the y limit from 0 to 1 minus z. If we integrate with respect to dz dy, your y limit must be a constant. So take the y equal to 0 to y equal to 1 to be the y limit. To find the z limit, you need to follow the z direction. So with that, you obtain the lower z limit here, which is equal to z equal to 0. So this is the lower limit. And then you continue. So this is another curve that represented by this equation. So this is the upper limit, which is equal to 1 minus 1. So you can see that your dA can be represented by dz dy or dy dz here. If you choose dz dy like this case, then you should choose this limit here. On the other hand, if you choose dy dz for the area, then this is the corresponding limit. With that, it's success to form the equation to find the mass by using the triple integral. By solving the integration, you obtain the mass, and you can see both of them are equal. In this example, we are going to use the type 3 triple integral to solve the previous problem, which is to find the mass for this object with the density function equal to x, y, z squared. In this method, you need to integrate with respect to y first. So you need to find the y limit. So if you move from the y direction, then you will meet this curve. This curve is given by y equal to square root x. Therefore, this is your lower limit. So we can substitute this by square root x. Then you continue to move in the y direction and meet another curve. And this curve is given by this equation, where you can find the y equal to 1 minus z here. Therefore, this is your upper limit. So substitute inside 1 minus z, then you should obtain this equation. To find the area of the region, you need to imagine yourself to be here and see the object from the y direction. So you can see this point will be remain, and then this point project to the zx plane here. So you continue. You can see there is a curve like this, right? So if you plot this curve in the zx plane, then you obtain this. This function here is the intersection between this curve and this curve. Therefore, we can substitute the y inside to obtain z equal to 1 minus square root x. So this is the equation for this line. Therefore, in the zx plane, this curve is represented by 1 minus square root x equation here. From this equation, when the x is equal to 0, your z will be equal to 1. And when the z equal to 0 here, substitute inside, you should obtain your x equal to 1. We can find the area of the region by using dz dx or dx dz here. So if you integrate with respect to dz dx, then you need to ensure the x limit is a constant. For example, here your x limit is equal to 0 to x equal to 1. Therefore, you have 0 to 1 for your x limit. Then you continue to integrate with respect to z. So z is equal to 0 here. So this is the z direction. And if you continue, the upper limit for z is 1 minus square root x. Therefore, the z limit is 0 to 1 minus square root x. On the other hand, if you represent the dA equal to dx dz, so in this case, the z limit must be a constant. So your z limit is from 0 to 1 here. Therefore, this is the z limit. You continue to find the x limit here. So x limit can be found from this direction. Therefore, you have the lower limit equal to x equal to 0. And the upper limit can be found from this curve. So from here, your x is equal to 1 minus z power of 2. Therefore, you can substitute the lower and upper limit inside. After you compute the triple integral here, then you can get the answer for the math. So far, we have successfully solved the triple integral problem that involve the type 1, type 2, type 3 method. You can see that same solution can be obtained by changing the order of integral here. The tricky part here is to find the limit that require the imagination of the region. This is important. Please master this. In this example, you are going to solve this triple integral where the function of x, y, z are given, which is equal to xy squared z cubed. We know that this is the density function, and the dx, dy, dz here represent the volume. So if you multiply density function with the volume, you are actually computing the mass for this object. This object is bounded by the following surface from the z equal to 0 to z equal to xy, which is from the xy plane here, which is the z equal to 0, and then to the curve here, which is z equal to xy, and then it's also bounded by the x equal to 0 and x equal to 1. So x equal to 0 is the yz plane, which is over here, right, to the x equal to 1, which is over here. This object is also bounded by y equal to x, which is over here, and also the y equal to 0, which is the xz plane. Let's continue to solve this integration. There is correction in the note. This is the corrector step. From the boundary of the x, y, z given previously, it will be convenient for us to perform the triple integral with respect to dz, dy, and dx. Because you know that the outer part, which is the integration with respect to dx, must have the constant limit. So in this case, x is suitable because you have constant limit. And the inner part must consist of the function in terms of two variables. So in this case, z limit has the function in terms of x and y variable, therefore is suitable to be integrated inside. And then the y limit here has the function of x. If you integrate the function with respect to z, you need to ensure the xy square here is constant, and integrate z cubed, you obtain z to the power of 4 divided by 4. So substitute the limit inside, so your z equal to xy, substitute inside here, you should obtain x power of 5, y power of 6 divided by 4, minus with the 1, substitute with 0, so you obtain 0. So you continue to integrate this with respect to y. So y power of 6 will become y power of 7 divided by 7. And then you substitute y equal to x inside, minus with the 1, substitute y equal to 0. Then you should obtain this. So you continue to integrate this with respect to x. So you obtain x power of 13 divided by 13. And this, substitute the constant limit inside, then you should get the final answer. In this example, we are going to find the center of mass of this solid with the constant density that is bounded by the parabolic cylinder x equal to y squared. So this is the function where x is equal to y squared, and the plane x equal to z, which is this curve, z equal to 0, which is the xy plane here, x equal to 1, which is this plane. The formula of the center of mass is given by this formula, where the moment can be obtained here. And we have learned how to find the mass by using the triple integral. Since the region in the xy plane are given, therefore you are looking the object in the z direction. Therefore we integrate the z direction in the inner part here, where the z limit is equal to 0 and z equal to x here. So you substitute the lower and upper limit. To find the area of this region, you need the intersection point here. So you can find these two intersection points by let the equation 1 and equation 2 here to be the same. So substitute x inside this equation, you obtain y squared equal to 1. Therefore y is equal to plus minus 1. With that, you know that here your y is equal to 1, and here your y is equal to negative 1. So this is the lower limit and upper limit for the y. Therefore, when you integrate with respect to y, the lower and upper limit is negative 1 and 1. Then you can continue to find the x limit in this direction. So this is the lower limit, which is equal to x equal to y squared. So this is the upper limit for x, which is equal to 1. Therefore, substitute the x limit inside for the dx. By solving the triple integral, you obtain the mass equal to 4 rho divided by 5. Then you can continue to solve this to find the moment. You can see that the moment formula here use similar formula as the mass formula. To find the moment about yz plane, you need to multiply the mass formula with the x. To find the moment about xy plane, then you need to multiply the z with the mass formula. Similarly, to find the moment about xz plane, then you need to multiply the y with the mass formula. If you compute this, you should obtain 0 for the moment about xz. So 0 moment about xz plane divided by the mass will give you 0 center of mass at the y coordinate. So you can see that for this object, since this is symmetry, therefore the center of mass to be located in this line, where the y bar is equal to 0. So if you continue the calculation here, you should obtain the corresponding moment. Moment about yz divided with the mass here, you should obtain 5 over 7, which is the center of mass in the x direction. So the center of mass to be located around x bar equal to 0.71 here. Lastly, if you take the moment about xy, divide with the mass here, then you should obtain this answer, and this is the z bar. So your center of mass to be located somewhere here, where the x is equal to around 0.71. Your y is equal to 0, which is in the x-axis, and lastly, your z is equal to around 0.357. So around this point is your center of mass.